you.
Thank you.
Welcome.
Hello.
Your head is
big.
You know who I am. Yeah, good guess.
Okay, I see the flower.
Yes, I got it. Sabrina gave it to me.
Oh, was it hers or yours?
It's Sabrina's because
Oh.
Sarah Jessica Parker always has a huge flower.
Mm-hmm.
She got
I have to.
rocking her flower. She is so
Just
sweet.
kidding.
I don't know why, but I think of like Wendy. Whenever I see Wendy Wen, I think of SJ.
Oh, wait.
They look like her.
Who's
Yeah.
Spencer's?
I got it, yeah.
I don't know. That's always like-
Yeah,
What?
then we didn't even plan.
No, Lauren, who are you?
I
From
Cinderella
Cinderella
story.
With who died.
Oh, yeah.
Her name's
Yeah, that's really good.
I love that
like
movie.
Sam.
Thank you for that.
Yeah.
I can't do that.
I don't
There
think
you
I
go.
know.
I don't
Me
do
too.
like, it's bad.
My breakfast.
We got a lot of.
Oh my gosh, I love it.
What?
I love it. Thank you. Who are you?
From Carly Rae Jepsen.
You need the ones with like the buckle
I
on
know she
it.
has yellow ones. Those I don't own yellow heels.
She has yellow heels.
Yeah, she owns yellow heels and she wears
That's
ones for exercise.
funny.
I don't really know.
Oh,
It's
did
actually
you,
really
did you
fun.
get like a serious road burn?
You would have
They're big like socks.
Oh, that thing was so rude.
Are you wearing Snapchat? Okay, I guess.
Yes.
Somebody came in.
Oh,
I
we went to
These look like
Taco Bell,
something special.
and then
That never ends well, Allie.
I don't have any special.
The rest was
I was like, oh, I need to.
I have like
So
one
you're
pair of
like
slacks
perfect
and they're
I
black.
was like, I don't want you to
And I was like, that's
And
fine.
then Dawn was also like, oh, let's go home. And then like 10 minutes later.
Does it look weird with the camera? Are you sure you don't?
It doesn't black.
I don't either.
Just making sure I don't know what you
Can't be born.
And then Austin realized what I was. He didn't realize what I was. Last night.
It doesn't look.
After the
It is
broke
huge.
up, and he was like, oh my God.
Actually, it would probably be like, God, get your head out of my way.
Yeah, he's like, oh, you close the eyes. I was like, what is that? I was trying to.
That's like,
You should have really dressed up as
face.
I was like, I was trying to.
One,
teach you
really
everything.
big.
Looking.
One food drink.
Olivia's the one that I
Dressed up like a
I
guy.
can tell what that.
You should have said for the guy. That was
Yeah.
Sure it is.
Feels the
Freaking
growth
gross.
parts. Yeah, I know, I'm a person.
You should have.
Should we
Exactly.
just like shit anything? Oh, you're just doing I'm looking for you guys, girls. So go ahead.
I'm sure it's something just slide back.
No, I know. Okay. Oh, my gosh.
Genius.
Oh, who are you? Oh, who are you? Oh.
Wait, here's your phone.
Who? From, who are you? I see it. Who are you?
Is this what it's called? Okay, when we were in the midst of discussion yesterday, we were sort of giving examples for the two major classes of nuclear reactions. And in one case, we start with a big atom, like uranium, and broke it into two smaller atoms, like krypton and barium. This is an example of a fission reaction. What I always think of when I think of fission is the word fissure, which is a crack. There's some cool pictures online if you search fissures, where there's a crack in the Earth's crust and lava coming out of the entire crack. It's kind of neat that you have like a wall of lava as opposed to normal volcanic eruptions coming out of, say, like a single point location. Sometimes, however, we have two small atoms coming together to make a big atom. This is an example of a fusion reaction. You can think of this because the word fuse, to fuse things together, is to make two things come together. If you took, well, if you ever played with Play-Doh as a kid, maybe you fused together two colors of Play-Doh to form a color in between.
There's like a drink called
like fruity or something and has like lots of different fruits in it.
There you go. So they like fuse a lot of different flavors into one drink. So the word fusion has is aptly chosen, I think, for this case. So one example of a fusion reaction that we gave yesterday. Oh, okay. Is the reaction that occurs in the sun, which is two heavy isotopes of hydrogen forming together, fusing together, I should say, to form helium. Normally speaking, this is not always, but normally speaking, fission reactions involve a certain amount of release of energy. Fusion reactions, in terms of the energy that's given off by these reactions, a fission reaction, while still letting off a large amount of energy, fusion reactions let out significantly more. To give you an example, this reaction that occurs on the sun actually has occurred on Earth. We've made atomic bombs that are fusion bombs. We call them hydrogen bombs because they use hydrogen as their fuel, and they fuse hydrogen together to form helium. One aspect of fusion reactions is normally you have to be at really, 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 really high temperatures, like sun-like temperatures, in order for these reactions to occur. So you think, well, how does this happen? Well, I just want to give you an idea of the amount of energy that's given off from these reactions, the amount of energy that's required for these reactions, for that matter. We had a fission bomb that involved uranium-235. And what started the uranium-235 reaction? A neutron, right? That's our fission bomb. We flick a neutron at uranium and the chain reaction starts. The neutron is the detonator. We start with a neutron and it detonates the bomb. For the fusion bombs, here's the fusion bomb. This is going to be using the hydrogen isotopes that we talked about. The detonator for this is a fission bomb. So you've got to take one of these uranium atomic bombs and put it inside the hydrogen bomb, so that when the uranium bomb goes off, there's enough heat and energy for the hydrogen to fuse together. So to make the analogy, neutron is to fission bomb, as fission bomb is to fusion bomb. Terrifying. Terrifying. To give you an idea of the relative strength of these things, I'll pull up a fairly famous internet picture. As I say this, I hope I can find the picture. I'm slightly nervous now that I've said that the picture is famous. But, let's see if I can find it.
Did you write Beetle on the album?
I love you.
You're the only person that knows that, I think.
Nuh-uh.
In this building.
Not really.
I'm obsessed with the Beatles.
No, that's beautiful.
Every album, I've got it.
Same with my dad.
Wait,
I just-
records?
Huh?
You have a-
I've been begging him, like, can you please get a record player so we can play vinyl?
Do you have like the records though?
No.
Oh, you don't?
My brother's got, like, the original from, like, '67, Sgt. Pepper's Lonely Hearts Club Band. Yeah, someone just
Wow.
gave it to him, and it's like $400 vinyl. Yeah.
My dad has like a bunch of their records.
They sound so, the record sounds so much better than.
There's a lot more there too.
Yeah, you can hear everything, every
Mhm.
instrument you can hear.
Okay, so this allegedly famous picture, I'm struggling with. It's frustrating.
But we watched a few hydrogen bomb like years ago when we
Wait, did you buy this to get?
We did.
Or no?
Yeah,
It's
it's
not
good.
cool. It's like,
I
like,
would
jeans.
think we should on my hat. It's cool. It's all.
Okay, this will give us an idea here. The yield here is in kilotons. That's, kiloton is the amount of energy that would be given off by 1,000 tons of dynamite. That's a lot. So the fat man and the little boy are the two atomic bombs that we dropped during World War II. And those are, that was their nicknames. Those guys are about 10 to the first power kilotons, so about 1,000 tons of
Oh my
dynamite, which, yeah, 1,000 tons is still 1,000,000 pounds of dynamite, that's a lot. Or 2 million pounds for that matter. Now, the hydrogen bombs are up here at 10 to the 4th kilotons. So they're 1,000 times more powerful than the atomic bomb that was dropped during World War II, or the two of them that were dropped during World War II. That is terrifying. 1,000 times more powerful. This is a logarithmic scale up here, so what looks to be close is actually every tick mark is a power of 10. So that's a huge, huge strength difference between the two. And to try to emphasize the strength difference, that's why I made this analogy. These fusion bombs require an atomic bomb to go off inside of them just for them to go off. I think that's an idea of, isn't that kind of terrifying? Awesome is one way to think about it. Yeah, I mean, it is the sun on Earth, literally. I mean, that's what's going on. Now, why energy given off, right? We have energy given off, but I think it begs the question of why. Like, okay, we're taking two nuclei and we're slamming them together and fusing them. Why is there energy given off? Let me give you a reason for why. Let me come over here and give you an example. Here's an example to explain why. This is one from the book, and I'm going to have numbers to back myself up here. And that's why I'm choosing this example from the book. So we're going to take lithium with atomic mass 7, and we're going to bombard it with good old-fashioned hydrogen, atomic mass 1, and we're going to form 2 helium nuclei. Frankly, I'm not sure whether we would call this one a fusion or a fission. I guess maybe fission. We start, the biggest one is lithium, and then we break apart into 2 smaller things. Normally it would be more clear as if I would ever ask you, is it a fission or a fusion reaction, it would be rather clear as to the case. But here, now I'm going to mention the masses of these things. Lithium, if we measure its mass, has a mass of 7.0144 units. That's U for atomic mass units. We're measuring single atoms here. And we're not going to be rounding off the mass at 7 like we have all year long. We're going to be really, really specific. We're going down to 4 decimal places. The mass of the hydrogen is 1.0073 atomic mass units. And the mass of each of the heliums is 4.0015 atomic mass units. Now you might be thinking, well, Mr. Blythe, you told me at the beginning of the year we just want to round off the numbers and just work with the numbers as simply as possible. Yes, normally, but in the case of a nuclear reaction, we want to be very precise, and I will show you why. Let's add up the mass of what we started with and the mass of what we ended with and compare them. Now, think about this. If you're going through a chemical reaction, you take water and salt, or water and Alka-Seltzer, you mix them together, what you start with and what you end with should have the exact same mass. Like when you pour the milk in the cereal, does the weight of the milk add to the weight of the cereal? I hope. Is the weight of the cereal and milk together equal to the weight of the cereal plus the weight of the milk? I hope. If not, you're pulling some crazy magic trick every day whenever you make your cereal. I mean, think about it. What goes in should equal what comes out, right? I mean, right? Well, think about that. Let's put this together. 7.0144 plus 1.0073. Add those guys together. That's 7.120. 8.0217. Go to the other side. We have two heliums. 4.0015 plus 4.0015. 8.0030. What the heck? We start with 8.0217 mass, and we end with 8.0030 mass. We lost mass. How much did we lose? A certain amount. I'll do the subtraction, this one on my calculator in my phone, so I don't want to have to think too hard about this. 8.0217 minus 8.0030. 0.0187. This is mass lost. I mean, I'm saying question mark exclamation point because it's like, wait, what's going on? Like, this seems magical. It's actually not magical, it's scientific, but until the 1910s, we did not have an explanation. In fact, this particular experiment was not specifically conducted and verified until 1932. The reason is this oh so famous equation that I'm sure you've seen before. E stands for energy. M stands for mass. And C is just a constant. Some people try to say that it stands for celeritas, but that's totally bogus. Celeritas for a celestial number, because they, like Einstein had a like almost like a mystical value on the speed of light, which actually is what C is, but C stands for constant. Some people say it's celeritas, like the number of the heavens or something, but that's kind of an absurd notion.
The number of the heavens?
Yeah, because the speed of light is kind of important when you look out into the heavens and you like watch the stars. Technically, the light's been traveling to you at the speed of light for many, many years. I think that's where the motive for saying C is celeritas, but if you ever hear that, that's totally bogus. C stands for constant. Just to let you know. But the C is just a constant, it's just a number. The C squared is always the same number. What's interesting here is that energy and mass are equivalent. Where did the mass go? It turned into energy. So what Einstein's equation says, basically, in words, is that energy and mass are interchangeable forms. So, in other words, if you lose mass, you gain energy. And that energy gain is given off, in most cases, in the form of heat, in the form of an explosion of some sort. And the energy that's given off from the breaking of the uranium atom is the energy that's harnessed in the bomb. Where does the energy come from in a nuclear reaction? The destruction of the mass. The mass is lost, the mass is converted, really, from mass to energy. So, nuclear reactions are the exception to the rule. The normal rule is, take the milk, take the cereal, put it together, the mass that you start with is the mass that you end up with. But in the case of nuclear reactions, the amount of mass between the starting reactants and the final products is different. And it's the difference in mass that explains the energy that's released. And it's Einstein's equation that gives us a framework by which to determine exactly how much energy is given off for a particular amount of mass. So we could actually take this mass number, put it into Einstein's equation, and multiply by the speed of light squared. The speed of light squared, by the way, we could give an idea for this. And the units are going to be a little bit challenging because just don't concern yourself too much with the units, but just look at how big the numbers get. We lose 0.0187 of mass. That's a really, really small number, right? 0.0187. If we were dealing with moles here, like a mole of lithium and a mole of hydrogen making 2 moles of helium, we'd be losing 0.0187 grams. Now, think about 0.0187 grams. That is a really small amount, is it not? 1 gram is the mass of a paperclip. 0.0187 grams is like a speck of dust. Times C. C is 3 times 10 to the 8th meters per second. 3 times 10 to the 8th. So let me multiply this out. Oh, I gotta square that. Oops. So, yeah, right? That's a huge number, isn't it? 3 times 10 to the 8th? I don't even know if my calculator's going to let me do this. Holly, maybe you can help me out. So, if we do this in the calculator, we'll do 0.0187 times 3e8 squared. And I'm telling you this number's going to come out huge. Not small.
Where's the, what's the E?
E8, and then do times 3e8 again. And that'll give us a rather large number, I believe.
1.68.
1.68. Times 10 to the 15th. Okay, this will come out in joules. Now, what's a joule? It's just a unit of energy. But let me be clear. The amount of heat that's given off by a human body is 50 joules. That's also about the amount of heat that's given off by, for another example, an electric blanket. If you ever had an electric blanket, jack the thing all the way up, it gives off about 50 joules of energy. That gets you pretty hot, right? The electric blanket. So let's think about this here. 168. We got to hop the decimal place 15 times. That's going to add 13 zeros. Okay, so this is about the heat given off by an electric blanket. Ooh, how warm, right? This is the heat given off by the conversion of 0.01 grams of mass converting into energy. Right? So just to be clear, you can lose a very small mass and you can gain a huge amount of energy. Right? I mean, that's a lot. That's a lot. That's, to be clear here, that is a billion times more energetic than an electric blanket. And all we did was convert a piece of mass about as massive as a speck of dust into energy. So every speck of dust that you see, if you could harness the energy in that mass, you could have a billion electric blankets worth of energy. It makes you appreciate dust more, maybe. I mean, literally every dust ball could be, if converted into energy, converted into a massive amount of energy, no pun intended. Right? This is intense stuff, nuclear reactions. And the reason that they are intense is because they are the reactions that involve an exchange that we can witness of energy into mass. The sun is actually going through this type of reaction all the time. And eventually, the sun will run out of mass. And eventually the sun will then run out of energy, and it will burn out, basically. The fuel that the sun is using is mass, and eventually, if it's using mass for fuel, eventually it'll run out. I think that's the least of our worries right now, but it's something to just posit as a thought. Mm-hmm.
So if like this reaction is like happening on the sun like every second, what happens when there's like a solar flare? Is there anything different from your reaction, or like if there's more to it?
Yeah, so a solar flare, what you can think of as a solar flare, let me grab a picture of this so that we can see it. A solar flare is basically a pocket of concentrated, where the reactions occurring on the sun happening at a relatively normal rate gets concentrated in one area. So it would almost be like if you're kindling a fire and like one spot gets extra hot and like sparks shoot out. It would be very similar to that. It's basically a natural consequence of having a flame on that scale, if you think in those terms. Solar flare, that's kind of a, part of me is not fully satisfied with my explanation, and I feel like I should be able to explain that better, but that's about as, so there's a, and this is a fairly famous picture. Oh, that one is cool too. So the idea here is this is the surface of the sun, and then there's a flare of. Now, what happens here with solar flares, to be clear about this, is there's some people call it the fourth state of matter. If you heat up a solid, it'll form a liquid. Heat up a liquid, it'll form a gas. Heat up a gas, you can get it hot enough. The gas will actually give off all of its electrons, because the gas will be so hot and have so much energy that it'll have the electrons in that gas will have too much energy to stay around the nucleus. They'll actually, the electrons will start to float freely, and what you'll then have is just nuclei, like naked nuclei, that will be positively charged. And so a plasma is basically a gas that's been heated up so much that it naturally forms ionized particles. These solar flares are so hot that they naturally give off ionized particles. The sun actually always gives off ionized particles, but a solar flare will give off ionized particles at an unusual rate. I mean, this solar flare is probably a few 100,000 times larger than the Earth in terms of the volume of sun that's flaring out there. Now, what that ball of ionized particles do is it will be given off, and fortunately for us, we have two things. One, magnetic field around the Earth, and two, an atmosphere, because the magnetic field will assure that those charged particles only are attracted to the poles, and the atmosphere will ensure that when those charged particles fall to Earth, that they're going to strike the atmosphere and not strike us. Because if those charged particles got to us, we would get sunburn on a level that our body probably couldn't take. We might have cancer cells being formed. But when those charged particles hit the nitrogen and oxygen in the atmosphere, all they do is excite the nitrogen and oxygen in the atmosphere to render a glow, which is a much nicer reaction than would occur. It's either we have an atmosphere and a magnetic field, and we get oxygen, nitrogen particles rendered a glow. If we didn't have those things, we'd get some skin cancer from the sun. When those particles do render a glow, I probably spelled that wrong, but Google will pick up the slack. Yeah, you've probably seen pictures of these things before. All an aurora borealis is the charged